Hello everyone. In this video we're going to discuss chemical nomenclature, or how to name chemical compounds, because there are certain naming systems depending on what type of compound you have. So for this video we're going to focus explicitly on those ionic compounds. Now again, ionic compounds, our root here is ion, so we're going to have two oppositely charged ions that when they're combined together are going to form a neutral compound. So in the last video, we discussed an example of Na plus and Cl minus. We have 1 plus and 1 minus. These are going to negate each other, and they'll have a neutral charge when they are combined. So 1 plus and 1 minus gives me 0. That's perfect. So how do I name NaCl? Because if you're a chemist and you just say NaCl, that might work for something that's relatively simple, but what if you have something that's more complex? Maybe something like NaCH3COO, right? There's a lot more elements here to name, and we have to make sure we know how to approach each of these formulas with the correct name. So I can say, for example, sodium acetate instead of NaCH3CO2 or COO. That's a lot more complicated. So we have to follow a system. Here's how you name ionic compounds. The first thing you want to do is name the cation first, followed by the name of the anion. So here's what we're going to look at. Na plus, what is Na? Sodium. So that's the first half of our name. We're already halfway done with it. Notice there's no prefixes here. We just literally name what the element is, or in this case, what the ion is, and that's it. Next thing we want to do is name the anion that comes after. Now, if you look at your periodic tables, Cl is chlorine, right? Chlorine is Cl. However, we're not going to call this sodium chlorine. Because this is an anion here, we're going to replace this suffix with a D instead of an N. So they should end in an "ide" ending. So that's where we get sodium chloride from. Again, notice there's no prefixes here, or nothing to indicate that it's one Na and one Cl. And the reason for that is because there's only one possible combination of sodium and chlorine to combine together. I can't have NaCl2 or Na2Cl, right? And I want to make sure that it's simple. That's where we're talking about that empirical formula earlier. So when we do ionic naming, we just name the cation first, the anion second. The anion must have an IDE ending. So really, it's nothing too crazy. Next thing we have to look at too is if we're naming polyatomic ions. So if you have a polyatomic as your cation, you're just going to name it, which there's not many. Specifically for this class, we need to know that NH4 plus is ammonium, so you would just say ammonium chloride if it's NH4Cl. Or up here, we have a polyatomic that is an anion. So we would just say sodium acetate. So if you see in a compound that there's more than one capital letter, and specifically your first thing is a metal, it's a pretty good giveaway that you have some sort of polyatomic ion in your list. And then that references back to your memory with what polyatomics mean, what names. So here's some examples to kind of show you what we mean. So again, sodium chloride was the example we just did. I want to go over the ones that have numbers next to them. So for example, CaI2. Notice the first element is calcium. We name calcium. The second element is iodine, and we have two of them. But notice we just name it iodide. So the naming is relatively straightforward for ionic compounds. You literally just name what each thing is. Now again, how do I know this is ionic? It's metal plus nonmetal, right? The metal's positively charged. It's on that left-hand side of the staircase on the periodic table. The nonmetal is to the right-hand side of the staircase, and it inherently gains electrons and gets a negative charge. So no matter how many numbers you have of each, just check your first element. Is it a metal or is it a nonmetal? Since all of these are metals, we're going to follow the naming system of just naming what we see. Now going from the reverse of a name to a compound is a little bit more challenging, because we have to keep in mind that we have to balance out the compound accordingly. So let's look at an example of that. Let's say we had magnesium, and let's go ahead and say it is magnesium sulfide. Let's say we have something like this. So we can look at our periodic table, and we would deduce that magnesium is Mg2+, because this is in group 2 on the periodic table. And remember, group 2, those alkaline earth metals, those are going to have a 2+ charge. Sulfide is in group 16. It's in one of those chalcogen family of elements. It's right below oxygen. So sulfide is S2-. Now I have to combine these. If you were to do the crisscross, you would get Mg2S2. However, this is not correct because we have to make sure that these subscripts are the lowest possible amount. You can divide both of these by 2. So we can instead just say MgS. And that's how you would approach one of those problems. Okay, so you basically have to do the inverse where you have to figure out what the ion is and then balance out their charges so that when you combine them, you overall have a charge of 0. It needs to have a net charge, that of 0. Okay, so there's a couple examples there. Let's look at polyatomics, for example. Again, it's the same type of thing. You just need to make sure everything balances out. So let's look at calcium sulfate, for example. Calcium is this first element here, and then SO4 is a unique combination, which is sulfate. So I just named what I see. Calcium sulfate, aluminum carbonate, magnesium phosphate, so on and so forth. Now again, you could also be given a name, and you might have to do the reverse. You might have to go from name to compound. So let's do a quick example of that. Let's say we had, let's say sodium, oops, don't happen there. Sodium hydroxide, a very common strong base. It's also known as Li. So, how can I figure out which charge is which? Well, I know that sodium's a metal, and I know this isn't a polyatomic, so that's indicating to me that OH should be grouped together. Sodium is in group 1, so that means sodium has a +1 charge. I have 1 sodium and 1 hydroxide. If sodium's 1+, and I only have 1 sodium, I have 1 hydroxide. What does this charge of hydroxide have to be then for it to equal 0? Could it be -1? Yes, it can be, because +1 and -1 would balance out. Let's look at another example. Let's say I had magnesium chlorate, MgClO3, and then a 2 there. Can we figure out what the charge is on both of these? I can reverse crisscross. I have only 1 magnesium, and I have 2 chlorates, right? Because this little 2 there is indicating that to me. So, I have 2 chlorates that has to equal the same thing as 1 magnesium. So let's reverse crisscross it. I know that if I had a 2 up here, I would drag it down here if I was crisscrossing. So that indicates to me that magnesium then is 2+. If I were to reverse the charge here, I have only 1 magnesium. That means that chlorate has to be 1-. So I would have to have 2 minuses, a ClO3- and a ClO3- to balance out with a 1 Mg2+. Now everything is working out nicely. So now this is good and balanced. And again, that was magnesium chlorate. Don't worry, with more practice and more studying, this will become second nature to you. Let's look at what happens when we have an ionic compound that contains a unique metal ion that has a variable charge. Now, if you remember back to last year in chemistry, you may have received a periodic table of ions that you used either to study from or used during class. You would find that many transition metals often found in periods 3 to, I think 12, 3 to 12, if I'm not mistaken, somewhere in that ballpark. You'll find that these elements here often have multiple possible charges. That means, for example, iron readily exists as iron 2+ and iron 3+. And this poses a bit of a problem, right? Because when we name elements in chemistry that are ionic in nature, we have a metal and then a nonmetal, we don't specify the charges. We assume we know what the charges are because many of your representative elements, your 1 to 15 through 18 type thing, all of those, we understand what those charges are. Like, we know what those are. So we have to make sure that we specify if an element, usually a metal, has multiple charges. So let's take an example. Let's say I had a FeO. Okay? I could have FeO, or I could have Fe2O3. Both of these are correct combinations of iron and oxygen. What's the difference? The difference is the charge on the iron, and I have to specify that. So let's do some backward thinking, and let's see if we can figure out what the charges are. Oxygen is in group 16, which indicates to me that that charge is going to be 2 minus, no matter what, right? So if I have, let's look at this one first. I have 1 oxygen and it's 2 minus. I have 1 iron. What does iron have to be to balance this out? It has to be 2 plus, right? So then when I would write this name out, I would say iron, and then I'm going to put Roman numeral 2, and then name the anion oxide. Now this Roman numeral 2 corresponds to the charge. So it's not the number of irons. Notice there's only 1 iron here. The Roman numeral, again, corresponds to the charge. So let's look at this one over here. I have 3 oxygens, and oxygen has a charge of -2. That means overall, this anion portion is contributing a charge of 6 minus in total. So if I look at iron here, I have 2 irons. 2 times what would give me 6 plus, or positive 6? 2 times 3 plus would give me that. So if I were to name this element, I would have to say it is iron Roman numeral 3 oxide. And again, keep in mind, this Roman numeral 3 represents the charge. That is where that's coming from. Now again, this isn't for all transition metals, but it's for a lot of them. There's some other ones where you're not going to necessarily have Roman numerals. I encourage you to look over your list and see if you can figure out which one of those are to kind of help you remember. A couple examples of that: silver's a good one, and zinc's a good one that you often see where they don't have Roman numerals. So I'll write no, and I'll put a little Roman numeral symbol there for those particular metals. Here's some examples to kind of show you what I mean. So notice here we have 2 examples of iron chloride. We can have iron 2 chloride or iron 3 chloride. Here we have 2 different versions of mercury. Here we have mercury 1 oxide, and here we have mercury 2 oxide. Again, that is representing the charges. So in this case, iron has a charge of 2 plus. Here it has a charge of 3 plus. Mercury here has a charge of 1 plus. Mercury here has a charge of 2 plus. Keep in mind, these anions are staying the same. Chloride is -1, chloride there is -1, O is 2 minus, O is 2 minus. So do you see how this balances out? Here I have HgO, 2 plus and 2 minus equals 0. 2 times 1 plus is going to balance out with 2 minus. Same thing here. I have -1 and -1. That's telling me that this tin has to have a 2 plus charge, which is indicated by the Roman numeral there. And the tin here has to have a 4 plus, which again is indicated by that Roman numeral 4 there. Another thing we want to look at is specifically when we name ionic hydrates. What an ionic hydrate is essentially an ionic compound. So I'll go ahead and put a random XY combo here. Okay, this could be any combination of metal to nonmetal. But what happens is you can have a crystal form in which water molecules are bound to it. And how we represent that is we put a big dot here, which is not a multiplication sign. Rather, that indicates that we have a hydrate. And then after, you'll have some number, and I'll go ahead and put N, whatever that number is, of water molecules. So it's an ionic compound, big dot, and then some number of waters. That's a dead giveaway that you have some sort of hydrate. Hydrates are convenient because if you're actually in a chemistry lab, it's a lot easier to handle a hydrate than a liquid form. It saves some money too on shipping and things like that, and it allows chemists more control for how concentrated they want their solutions. You don't need to know that for the course, but that's just in case you wanted to know. So, hydrates may typically be dehydrated by heating them to remove the water molecules, yielding what's called an anhydrous compound. Again, anhydrous, an is a prefix meaning without, without hydra, without water. So it's an anhydrous compound. To name hydrates, we name the anhydrous compound per usual rules. So we're going to name the ionic compound first with how we're familiar. Then you're going to add the word hydrate with a Greek prefix denoting the number of water molecules. Now, what are your Greek prefixes? Those are back here on this slide here. You have to know these prefixes not only for naming hydrates, but also for your molecular compounds, because these play a huge role with your molecular compounds because they don't use the same rules as ionic ones do. So 1 is mono, which sometimes is omitted. For molecular, we'll go into the rules on that. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So these would look very familiar because these are the same prefixes we often use in geometry classes. So again, just familiarize yourself with these, that way you become very familiar. Usually students get these later ones more confused. Okay? So let's look at a few examples to kind of show you what we mean. So copper 2 sulfate, that is naming this compound right here. See copper 2 sulfate because sulfate has a charge of 2 minus. If I have one group of sulfate, I have one group of copper that has to be 2 plus. Copper 2 is coming from that 2 plus sulfate. And then pentahydrate. Notice, penta means 5. How many waters do I have? I have 5 there. Calcium chloride, pretty simple, it's right there. Big dot. Monohydrate. Mono means 1. Notice it's just 1 water. There's no number there. You could put the number 1 there if you wanted. You wouldn't be wrong if you did. But generally, when we have the number 1, we often omit that from the formula and from the compound. Thanks for tuning in.